Good morning, everyone. Am I audible? Okay, good morning. So let us begin. Today we are going to be talking about a few more sorting algorithms. So previously we looked into three different sorting algorithms, which were selection sort, bubble sort, and insertion sort. Today we are going to be looking at uh, merge sort as well as quick sort. But before that, let us first review what we looked at yesterday, and then we are going to begin. Okay, so if I am audible and the screen is also visible, let us begin. Thank you all for your responses. Okay, so yesterday we looked into time complexity first, and we said that all elementary operations, such as let us say multiplication, addition, load, or store, they are going to take unit time, right? And then we moved ahead and we talked about what kind of algorithm is an ideal algorithm in consideration to the time complexity. So we said that any kind of algorithm which is going to process a very large input in less time and give you the desired output, that is going to be considered as something which is more of use to us, because it is going to process a large amount of input in less time as compared to any other kind of algorithm, which is going to take more time, right? Then we looked into certain examples and we considered the time complexity. We also looked into recursive functions and how you can calculate the time complexity as well as the space complexity. So say for example, here we had this a piece of code wherein there were two nested loops. So if you run these loops starting from 1 to n, you are going to achieve a time complexity of order of n square. Then we looked into a recursive code example wherein you were calculating the factorial. So we looked into how can you calculate the time complexity for a recursive function, and so on. So we went ahead and looked into the space complexity as well, and we said that if we consider the stack space, if we consider the recursive calls, then we say that here the time complexity will be depending upon the the space complexity will be depending upon the recursive calls that are being made, right? So in this particular example, actually we saw that this is how the space complexity is calculated, but in actual terms. So say for example, today we are going to be looking into merge sort and quick sort. So if you perform the recursive implementation of quick sort or merge sort, they are also going to take some space on the stack, but we are not going to consider that as extra space. We actually consider anything that has been taken as an array. Let us say for example, in merge sort we consider an extra array in order to store our sorted output, that we consider as extra space. Okay, so this was just an example to see that this is how recursive functions are going to be stored on the stack, and that is how you can consider the space that they take. Okay, now we started off by looking at sorting algorithms, but first we looked into the criteria that is going to differentiate or that is going to compare the different sorting algorithms. So we begin with time complexity and space complexity. We say if any particular algorithm does not require any extra space in terms of, let us say for example, an array, then we consider that as a in place algorithm. So in other words, if the space complexity is order of 1, we say that it is a in place sorting algorithm. And then we talked about stability. So we say that equal keys are going to maintain the same order after sorting. If let us suppose you have two values in your array where let us take for example 2, there are two occurrences of the number 2 in your array, and if after sorting the the value 2 which comes first in the original input array is going to again be in the first way when you actually traverse the array, then that is that means the if the order remains same, then it is going to be considered as stable. Otherwise it is not considered to be a stable sorting algorithm. And we also understood why stability is important. So we said that, say for example you have key value pairs, or say for example you have first name and last name that you want to sort, and then you actually use sorting on let us say for example alphabets or strings. In that case stability comes out to be of importance, but it is not really visible in integer array. But if you still haven't understood stability, then we can take up certain examples today and then look at how this thing works. Okay, then rest of the things you already know. We looked into bubble sort. We said that it is simply going to compare adjacent elements and swap them if they are not in correct order. And the space complexity here is order of n square, and this sorry, the time complexity is order of n square, and the space complexity is order of 1, which means that it is an in-place sorting algorithm, and we say that it is also stable. In selection sort, we always find out the minimum element, we place it at its correct position, and then we move ahead. And in insertion sort, we simply pick up an element, store it in a temporary variable, compare it with all the previous elements, and find out its correct position and place it. Right? We also looked into what are the time and space complexities for these sorting algorithms. Now, let us move ahead with what we are going to be discussing today. So before that, if you have doubts in any particular thing, then you can post your doubts in the group, and let me also know if you have understood stability. What does actually stability mean? If not, then let us consider certain examples and then look into how it works. Otherwise, let us move ahead. So yes, on the Telegram group, please let me know whatever you think should whatever you think should be the topic of discussion currently. Shall we move ahead with the new topics, or do you want to look into examples of stability, or do you have any other doubt? Okay, so the discussion for the test is going to be something that we are going to take up later on, because that is not our agenda for today. We can look into certain questions in tomorrow's class, because today we have to complete certain topics. But okay, so if I think some of you want me to explain stability, so let us move ahead with looking at that, and then we are going to start off with today's topics. Okay, so let me consider an array. Let me write down the example on which we are going to start off looking at it. Okay, so this is the example that we are considering here. So if you can see, we have two occurrences of this element 2, and so let us denote this 2 by, let us say, 2a. So the identification of this first occurrence of 2 is by a, and this occurrence of 2 is by b, let us say, for example. And let us now look at insertion sort, say, for example. So let us begin talking about insertion sort. So what did we talk about? Is insertion sort stable or is it not? Can you recall what we looked into from the previous class? Is insertion sort stable or is it not stable? Yes, can anyone answer that? Yes. So insertion sort is stable, right? Let us move ahead. Let us sort this array by insertion sort. So we are going to write down the array, what it looks like after every iteration. Okay. So first, what happens when you compare the first two elements? It is going to see if it is in the correct position or not, right? So you compare these two and see that 2 is already at its correct position, because 2 is less than 5 and it should appear before 5. So both of these are actually at their correct positions. So after, let us say, the first iteration, your array is going to remain the same. Now you compare the next two elements and you see that here 3 is less than 5 and it should be coming before 5 in the sorted array. So what do? You first copy 5 at its position. In a temporary variable, you store this value 3 and then first compare it with 5. So if 5 is greater, it is then placed here at its correct position, and then it is going to compare it with the previous element, which is 2. Now if 2 is less than 3, so it means that this is the correct position of 3. So the first swap that occurs here is of 3 and 5. Now both of these are at their correct positions, right? Now here you have 2b, 1, 6, 7, 4 and 9, right? So let us look at the next iteration. So the next pair of elements that are going to be compared is 5 and 2. So now you see you have these elements. In a temporary variable, this value 2 is stored and it is then compared to 5. Now 5 is greater than 2, so 5 takes its position and is copied here. Now what happens? You compare this temporary variable, which is containing 2, with the previous element. So the previous element here is 3. So what happens? 3 is again copied here at a position which is its index plus 1, and then t is again compared with 2. So now here you see this 2 is already equal to the temporary variable which is currently storing 2. So none of the changes occur. So you have 2b here. Okay. Now the rest of the array remains this way only. In the next iteration, you are going to compare 5 and 1 and then store in a temporary variable. You are going to store this value 1. Rest of the elements are currently in their own position. Now you compare this value 1 with 5 and you say that 5 is greater than 1, so 5 is copied here. T is now compared with 3. So this value 3 is now copied to index plus 1 position, and again you then compare with 2b. Now 2b is greater than 1, so 2 is copied here. Again you compare T with this 2. 2 is greater than 1, which is in the temporary variable, so 2 is copied here. And finally 1 is stored at this particular location, right? So similarly, now you keep on doing the same thing and keep on comparing the rest of the elements. So now you compare 5 and 6. 5 and 6 are at their correct position, so they are stored here only. After this iteration, the array is going to remain the same. Then you compare 6 and 7. 6 and 7 are at their own correct positions. Then you compare 7 and 4. So 4 is less than 7. So again, it is going to be placed at its correct position. So this time 4, 5, 6 and 7 and then 9. Now you see your array is sorted after the complete iteration and the complete loop are executed. You see that the order in which you had these values of 2, which is 2a first and then 2b, they are going to be in the same order in the final sorted array as well. So this is known as stability, and since we have performed insertion sort, we say insertion sort is a stable sorting algorithm, and you have verified it by actually using it on this. Okay, so this is about insertion sort. Let us consider and look at the same. So let us consider the same example, and this time let us try to run one of those algorithms which is, say for example, not stable. So which algorithm did we look at yesterday which was not stable? So we looked at selection sort yesterday. Yes, selection sort we said is a sorting algorithm which is not stable. So let us take up the same example here and let us consider the same example and see if selection sort is actually stable or not. Okay, so let me just copy these elements. So we have 2a, 5, 3. Then we have 2b, right? Then I have 1, 6, 7, 4, 9. 1, 6, 7, 4 and 9. Okay, so let us start off by talking about this, and let us now perform selection sort on this given input. So what happens in selection sort? How do you start off with the approach of selection sort? You find out the minimum element and then you place it at its correct position. So what is the minimum element among these? You have the minimum element here as 1. Now also please note that stability does not always mean that your order of elements is going to change every time. So it says stability means the order of elements may or may not change. So this term may or may not change is something that I would like you to focus on. It may or may not change, but if the algorithm is stable, then the order will not change. Okay. Yes, so let us move ahead with this. So we have minimum element as 1. Let us put it at its correct position. So you have 1 here, then you have 5, 3, 2b, and this is swapped with the element which is at its position. So we have 2a here. Now we have 6, 7, 4 and 9. Right? Now what happens? This part of the array is considered to be sorted and the rest of the array is now going to be considered as something which we want to sort. So we do not touch this particular element. We move ahead and look at the other element that we have. So now again, when we want to find out the minimum element, so how do you find out the minimum element? You go traverse the array and store the minimum element. If there is an element which is less than the current minimum element, you store it in the minimum variable. Okay, so we get 2b as the minimum element and we place it at its correct position. So the correct position of 2b is this. So we swap 5 and 2b. So we have this 2b, 3, 5, 2a, 6, 7, 4 and 9. Now simply we move ahead, we consider this part of the array as sorted and find out the minimum element in the rest of the array. Now we have this 2 as the minimum element and this is its correct position. So we swap 3 and 2. We get 1, 2b, 2a, 5, 3, 6, 7, 4 and 9. We consider this part of the array as sorted and we move forward, find out the minimum element, which is 3 this time, and now store it at its correct position. So we have 3, 5, 6, 7, 4 and 9. Find out the minimum element. Minimum element is now 4. So we store it at its correct position, which is where you have currently the value 5. So instead of 5, these two variables are going to be swapped. So this is going to be 3. You have 4 here. Up till here you have the array as sorted. So you have 6, 7, 5 and 9. Again you find out the minimum element, which is now 5. So you have 1, 2b, 2a, 3, 4, 5, 7, 6 and 9. Again find out the minimum element, which is 6, and place it at its correct position. So you have 3, 4, 5, 6, 7 and 9. And then finally you have this part of the array as sorted and find out the minimum, which is already at its correct position, and this is your sorted array. So now you see in this sorting, which is when I sorted this same example using selection sort, I found out that the order of these elements which have the same value is not same as it was in the original input array. So you had 2a first in the relative order, then 2b, but in the output array you have 2b first and then 2a. So we say that selection sort is not stable. Okay, so I hope now it is clear to everyone how stability works and why can we say that a particular sorting algorithm is stable or if it is not. Okay, so if there are any doubts, then go ahead and post on the group. Otherwise, let us continue and move ahead. Okay. So there is this question by Ria, which is, suppose we want to input 10 elements in an array and instead of using for loop, we use 10 scanf statements, then what will be the time complexity? So in that case, we say that since you are performing operations of order 1 10 times differently, so we consider that as it is actually going to be the same if we consider time complexity in that term, which is, say if you have 10 of these statements, the for loop is going to actually do the same thing for you, right? Why do we consider, again, let me just focus, I have already discussed this yesterday, n is something that we can have, n can even be 1. Even if you want to, let us say, take an input of a single variable and you use a for loop and you say for I is equal to 0 and I less than n, it is only going to, and n here is, let us say, 1. It is going to work only one time, but still you say that your time complexity is going to be order of n. What is the problem in placing this value of n as 1? It can take up the value 1, it can take up the value 10,000, it can take up the value as 40,000, 50,000, whatever, but it is going to remain order of n. The value of n is something that is going to change. Okay. In insertion sort, why 2b is sorted uh, before 2a? What do you mean by 2b is sorted before 2a? Try and run the insertion sort algorithm on the given input array, and then you will understand how this is happening. Okay, so let us move ahead today, and let us also, so as I said yesterday, we are going to look into some examples which are, let us say, going to take up time complexity in terms of log n. So let us consider that as well. So let us look into certain examples. So let me give you an example. In selection sort, why 2b is sorted before 2a. So what do you mean by why? It is how it happens, right? If you run selection sort on a given input array, it is going to, the way it works is something by which it is going to place 2b before 2a. That is what we were looking at. So this is what is stability all about. If you, so I don't think you were paying attention when I was explaining this example here, but anyway, you can go ahead, take up the same example and try to run selection sort on this and see how this is happening. Even if you write down the code and try with this same example, the same thing is going to happen. Anyway, let us move ahead and let us look at certain different examples and find out their time complexities. So say for example, you have this for loop here. Let us say this is starting from 1 and you are going on, let us say less than equal to n, and then you say I is equal to I multiplied by 2, and you do sum, let us say sum plus is equal to I, say for example this. So first of all, tell me what this will do. And what, then go ahead and tell me what will be the time complexity for this for loop. Let me write down another example as well, and then we can discuss both of them. So let us say I have a function. Let me write down all these variables. Okay, so we have these two examples here. Let us suppose I am calling this, so this is a loop which is, let us say, starting from I is equal to 1 going on up till I less than or equal to n, and every time it is multiplying the value of I by 2, right? So it is going to first run for I is equal to 1. The next time it is going to run for I is equal to 1 into 2. The next time it is going to run for 2 into 2, and so on and so forth, right? And this value of I, which you calculate after multiplying it by 2 every time, it should be less than equal to n, only then it will go inside the loop and run. So we say that here the time complexity is order of log n, And what can you say about the time complexity of this function here? So we have this method here which has an argument which is int I is equal int I, and let us suppose we are passing a certain value here. Let us say the value of I that we pass to this function is also equal to n. Then what will be the time complexity of this? So what will happen here, if you see, so from the main function, whenever you call, let us say, this particular function f with the value n, it is going to first declare an array and then check if I is equal to 0, and uh, then it is going to, let us say, call f of I by 2. So I, the value of I here is, let us say, n, so n by 2. The next thing it is going to call, let us say, is going to be uh, f of n by 4, right? So on so forth, like this. So you see here the time complexity here also come out to be order of log n. Now for all those who are unable to understand how this is happening, you can count, you can take up a value of n for, let us say, for this first example here, and see how many times it is going to run. And here the base of log that you will consider is going to be 2, because we are multiplying it by 2 here. And similarly here we are dividing it by 2. So we actually say that whenever we have n by, let us say, x, or n multiplied by x, in that case where x is a positive integer, so we also consider x as a positive integer here, and we say if it is greater than 1, the value of x is greater than 1, then the complexity is going to become order of log n, and the base here is going to be x. Okay, so this is a simple funda to understand. Just by looking at a for loop, or let us say a recursive function, you can decide what will be the time complexity. Now, so what basically happens here is, so there is something known as the master's method, which is actually something which is going to give you the correct time complexity of any particular algorithm that you consider, not only sorting algorithms, any algorithm that you write down. Master's method is something which is actually used to calculate the time complexity, but it is going to, let us say, take up a lot of time. So here we have just looked into certain examples like we did in the previous lecture as well, to understand how for now you can calculate the time complexity. Whenever now you're going to go ahead and study the algorithms course, in there you are going to understand the master's method as well. Okay, so it is quite a lot to understand when we consider master's method, and you will need a lot of examples for that. So we couldn't take that up for, let us say, this class, but for now I hope you have understood that. Okay, so looking at this and the examples that we have considered and the funda that we have understood, that let us suppose if you have n by x or n into x, where x is, let us say, a positive integer which is greater than 1, then the complexity is going to be in terms of log n, right? So this is something that you can remember throughout, and whenever, let us say, you have to see and tell the time complexity very quickly, then you can refer to this. Okay, so uh, let us now continue and look at merge sort. So let us begin by talking about merge sort, and then we will also look into quick sort algorithm. So up till now, if you have any doubts, go ahead and post them in the group and we will take that up. Okay. So is everything clear to you up till now? Shall we move ahead? So say for example, you have been given this array as input, and now you want to perform merge sort algorithm on this. So let us understand how what is the approach behind merge sort, and we are simply going to look at the way we discussed how each sorting algorithm works previously. We are going to do the same thing today, and then you can go ahead and as a part of your homework write down its code and try to implement it. Okay. Okay, so let us move ahead. So we have merge sort algorithm. Now what happens in merge sort algorithm? As the name suggests, here you are going to be merging. So let us understand what is it that you're going to be merging. So we say that, let us say for example, now if you remember we talked about divide and conquer approach of algorithms. So the same thing is going to be used here, which is that you are going to divide. So you have a problem, you have a big array here, and not that big, but anyway, an array here which you want to sort. So now you're going to break your problem into smaller sub problems. So here in this case you have a array, you have an array and you want to sort it. So you first divide it into sub arrays and then perform sorting on it, and then finally go ahead and merge the array back. Okay, so what do you do here? You divide your array into halves. Sorry about this. So you divide your array into two halves, considering the size, let us say here. So what is it that you can consider the mid as? So you say, let us say you have a left index and let us say you have a right index. So that divided by 2 is going to find out the mid element, and based on this you can divide your array. So you move ahead by dividing this array into half, and you have this as the two sub arrays after dividing them into two equal halves for now. So if say suppose your array did not have equal number of elements, then obviously let us suppose the first is going to the first half of the subarray is going to have 5 elements and the second half of the subarray is going to have 4 elements if the number of elements are not uh, equally divisible. Okay, so we have 6, 7 and 4. So your initial array is divided into two halves. Now since we are following the divide and conquer approach, we say that further you are going to divide this array as well. So the first thing that is done here is first you divide this array into two half subarrays. Similarly, you make recursive calls and keep on doing that. Okay. So you have now you divide this array into equal halves again based on this formula here. So you have 2a and 5, and you have, let us say, 3 and 2a. So the next thing which happens here is this. Okay, now you move ahead and you are going to, so for now just let us just forget that and see how this is happening. And now further again you go ahead and divide into sub problems. So this is how this is how the merge sort algorithm follows its approach, which is it is going to divide your array into sub arrays until there is only one element of each array is left. So you have this part of the sub array is again divided into two halves of equal size, and now you have reached a place where you have this as your, so this was 2a and this was 2b. Sorry about this. This is 2b 2b here. Okay, and similarly this half of the subarray is also going to be divided into chunks of same size 7 and 4, and further it is going to be divided into elements of size 1, subarrays of size 1. So you have 7 and 4. Now as you move ahead, what do you do here? You are going to consider each element, compare each element, and then you are going to have to place when you merge back. So now you have divided the complete array into sub arrays of size 1. No further division can now be performed. So what do? You start merging back, but before merging, what do? You simply compare two elements. So as you merge each element one by one, you are going to compare the values and see if they are merged in the correct order or not. So you see here 2a is merged. So when these two elements are merged back, you compare these two, and the smaller element is placed first in the merged part. So you have 2a and then 5, because 5 is greater than 2. Then again you move ahead, you compare here. So you have 2b and then you have 3. Okay, because 3 is greater than 2 here. Again you merge the rest of the sub arrays. So you have 1 and 6. Next you merge these two. So you have 4 and 7, right? So this is what you get after you first merge the sub arrays, and then now you are further going to merge these as well, these sub arrays as well. So you simply move ahead, and now you're going to compare each element with the rest of the two elements. Now you have in each sub array you have two elements, so you compare each element and then you place it at its correct position. So 2a is and 2b are actually at their own positions. So you have 2a here first and then 2b, because you see that 2a is actually equal to b, so 2 comes at its position, then 2b comes here, 3 comes here, and 5 comes here. Similarly, when you are going to merge these part of the sub arrays, you are going to have 1, 6, 4, 1, 4, 6, and 7. And finally, when you merge the two sub arrays, you are going to get your sorted output. Now there is another thing that you would want to note here, which is the order of the elements. I have taken an example wherein you had considered I had considered two elements with the same key, so that we can also check out on the stability of this particular algorithm. So we say that this is the final sorted and merged array, and we find out that this element 2a, which had occurred in this order only, 2a and 2b had occurred in the same order in the original array as well. So you have 2a here and 2b coming after 2a. The same relative order is maintained in the output as well. So we say that this sorting algorithm, which is merge sort, is stable. Okay. Now, this is the first thing that you have noticed. The other thing that you would want to keep a track of is if it is in place or not. So by in place, we mean that if it is considering any extra space, then you are going to consider that as an algorithm which is not in place. So we say that we are going to consider another array which is going to be storing our sorted output, right? So we say that this sorting algorithm is not in place. The space complexity that is considered here is order of n. N is the number of elements that you want to sort. Now in the sorted array, you are going to consider some extra space for the sorted array, which is going to contain the same n elements but in sorted order. So the space complexity is something which comes out to be order of n, and you say that it is, since it is considering some extra space, you say that it is not in place. And now let us also understand how do you perform it. So you simply say merge sort. Let us say you have this function of merge sort in which to which you are going to pass the full list of elements, which is the complete array of elements. And then what do? You simply call merge sort on the first half of the list and call merge sort. This is merge sort on the second half of the list. And after you have called merge sort on both the halves, what do? You simply merge the array back. So you merge the first half and the second half. Right? So this is simply the recursive calls that are being made, which is first you call the merge sort function with the full list, then you divide that list into first half and second half. So what happens here? You call this full list, this merge sort function with this full list, it divides into first half and second half, and then further for this half of the list you again call merge sort. Again it is divided into two halves, first half and second half. Similarly you go on up till no further division is possible, and finally when you've done that you call merge of the first half and the second half and simply give the output, right? So this is the approach behind merge sort, and you know it already that the time complexity for merge sort algorithm is n log n. Now, one of you has asked in the group what will be the space complexity. Okay, in example 2, let us look at that as well. So here the time complexity is log n. Now I want you to go ahead after the class and implement merge sort yourself and find out if your implementation is actually taking n log n time, which is used for sorting using merge sort algorithm. Okay, let us also consider uh, what will be the time complexity of this particular function. So now what is happening here? Every time you call the function, every time you are calling this function f, it is going to declare an array A of size n, right? So when you have this main function in the stack, you have the main function and then you call f of n. F of n is going to, let us say, take order n space. For the first function call that you make is order n space of array is going to be declared, and then you call f of n by 2. It is again going to declare an array of order n space. Similarly, up till all the functions are recursively called, right? All function calls are made. So how many times does this happen? How many times these function call happen? We have already seen that it is going to happen log n times, right? And now you are going to have every log n times that you are going to recursively call this function, you are going to have an array which is going to be of space order of n. So the space complexity here is going to be n log n. N because each time you are going to declare an array of size n, and you are how many times you are going to do it? You are going to do it log n times. So n log n. Okay. So shall we move ahead, everyone? No, merge is not a predefined function. You will have to define that. Shall we move ahead, everyone? Okay, so let us move ahead and let us talk about quick sort now. Let us take an example like we did for merge sort and understand how quick sort works. Okay, so let me write down an example and then we will move ahead with this. So say you have 20, 55, let us say 32, 14, 63, 393, let us say 42. Let us say you have these elements in your array. Okay, so let us say that you have been given this particular array. Now let us first understand the approach that is used in quicksort. So there are different kinds of approach when you go ahead and look at quicksort, which is, so every time that you are performing quicksort, you will have to decide an element which is going to be your pivot element. So we call that as a pivot element, and you are going to, so it is your choice which pivot element do you want to pick up. So pivot can be the first element of the array, it can be the last element of the array, or let us say any random element that you want to pick up. So there are different approaches based on that. The approach that we are going to look into today is going to be something which is considering the last element as the pivot element, and this particular approach of quicksort is the one which is most widely used, and it is defined and explained in a lot of books as well. So we are going to move ahead with that. We are going to consider the last element as our pivot element. Okay, so yes, so this is the first thing that you need to consider here. Now the next thing is that you are going to go ahead and compare each element with the pivot element. So this is the approach that you follow, which is choose, let me write down the algorithm as well. So choose a pivot element, compare it with other array elements, let us say, and based on the comparison you will have to perform certain operations. So let us say if you are comparing with a variable, let us say a of j, and you are comparing it with the pivot element, and a of j is greater than pivot, then you simply do nothing and move ahead. So let us say do nothing and go to the next iteration. Okay, and if a of j is let us say less than equal to the pivot element, then in that case what do? You increment an index, let us say I, and the next thing that you do is you simply swap the values a of j and a of I. Okay, and after, let us say, this loop, after let us say ending with loop j, you can place the pivot at its correct position. Okay, so this is basically the algorithm that you're going to follow every time. So what do? We consider an element as the pivot element, as I said, and what do? You say that I am going to compare each element of the array with the pivot element, and based on the comparison, I am going to perform certain operations. So basically, we want to find out the correct position of pivot. So we have considered this element 42 as pivot, and we want to now perform by comparing each element, we want to place this element 42 at its correct position. So if you can see in the array, you will find out that I think this is going to be the correct position for pivot. Why? Because you are going to have 20, 20, 32, no, 14, 20, 32 and 42. Yes. So we are actually going to find out the correct position for pivot and simply keep on comparing it with j. So we start j with the first variable. Let us say j is equal to 0. We are going to run a loop for j is equal to 0. And here we consider another variable, let us say I, and we initialize it to -1 initially, and we keep on comparing based on this condition. Okay, so let us move ahead. We know that this is j, this is p, pivot is the last element. Now let us move ahead and look at how it is going to happen. So you have j is equal to 0. So let me write that down. So you have two indexes, which is, let us say you take two indexes. Since you have low index as 0 and you have, let us say, high index as the number of elements -1. So let me also write down the indexes here, 6 and 7. So we have 7 as the highest index. You have this, okay, and the lowest index that you have is 0. Now, when you want to initialize pivot, you say that my pivot element is going to be A of H, which is the element at the last index, which in our case is 42. So you have 42 here as the pivot element. Now you run a loop, let us say for j is equal to, let us say, the starting from low index, which is 0, and going on up till let us say h -1, because h is the last index, and at the last index we have pivot, so we want to compare this pivot element with each element. So j should start from 0 and go on up till 6, because 7th element is the pivot itself. Okay, so high -1. Okay, now every time what do you do? So we start off with j is equal to 0, and we have the value of I is equal to -1 as we have initialized it. So let us write that as well here. So I is equal to 1, and now we begin. So once we begin, we are every time going to compare A of j with the pivot element. So we have A of j. In this case, we have A of 0, and we see if it is greater than or less than pivot. So pivot is 42. The element j is less than, the element at index j is less than 42. 20 is less than 42, right? So we say that this is less than equal to the pivot element, which is 42, which is 20 is less than equal to 42, right? This condition is true. So what do we do in this case? We first increment the value of I. We do I plus plus. So I was initially -1. Now I will become 0. And now we swap A of j and A of I. Okay. So I has now become 0. So A of 0 and j is also currently 0. So we say that we are going to swap the same numbers. Since I and j are the same values, there is going to be no change in my array. So let me write down the array again here after the first iteration. So we say we have 20. What was the next element? 55, 32, 14. 55, 32, 14. Then we have 63, 79, 93. 63, 79 and 93. Next element you have is 42. Okay, so 42 is our pivot element. Again, let me also write down the indexes here. So for everyone here, let me tell you, this process is going to be a longer one for the size that we have considered here. So at any point of time, if you have any doubts, then you can stop me right there, and then we will go over it once again. Okay. So you have this is our pivot element, and j is currently at 0. So j is here, and I is also at 0, so I is also here. Now the first iteration has completed, wherein we have swapped these two values. So the two values that we wanted to swap are basically the same. So no change happens because the value of I and j were actually 0. So now the next thing that happens is, in the next iteration we have j is equal to 1 now, and I is currently at 0 only. Okay, so I remains here and j comes here. Again, what do? We are going to compare the pivot element with this element, which is at a of j. So at a of j, which means a of 1, we are going to have this element 55, and we say that 55 is actually greater than greater than pivot element, which is actually 42, right? 55 is greater than 42. So what happens in this case? In our algorithm, we say that if a of j is greater than pivot, then we do nothing. Okay, so simply we do nothing and we move ahead to the next iteration of the loop. In the next iteration of the loop, we have the value of j is incremented, it becomes 2, but I is going to remain the same. So I stays here, right? I stays at this place. Now j comes here. Again, we are going to compare. So we say if a of j, which is now a of 2, if it is, so this is equal to, a of 2 is equal to 32, and is 32, what is the comparison between 32 and 42? So we say that 32 is less than or equal to the pivot element, which is 42. Pivot is also for now going to remain for this position only, which is 42. Okay, so we say that 32 is less than equal to pivot element, which is 32 is less than 42. So what happens in this case? If a of j is less than equal to the pivot element, then we increment the value of I and swap a of j and a of I. So let us do that. Increment the value of I, that is do I plus plus. So I was initially earlier 0, I will now become 1, right? And we say that we are going to swap a of j and a of I, which means swap a of, so what is j? J is currently 2, and what is I? I is currently 1. So swap a of 1 and a of 2. A of 1 and a of 2 have 55 and 32, right? So let us swap these two values, the two values that we want to swap. Let me denote them by circles, and these are the values that we are going to swap now. So in the swapped, after this iteration, what does your array look like? So you have 20, 32, 55, 14, 63, 79, 93 and 42. Okay, so we have swapped these two values. Now is everyone able to understand up till now? Any doubts to anyone up till now? We have swapped these two values, and this is what we get after the iteration that we have just performed. Okay, is up till now whatever we have discussed, is that clear? Shall we move ahead? Okay, okay. So for this iteration, okay, great. So for this iteration, we had the value of j is equal to 2. Now for the next iteration, we will increment the value of j. So j goes here, and I was earlier incremented, it had reached 1. So I is at 1, j has now come to index 3. Again, what do? We are going to compare a of j, which means a of 3, which is actually equal to 14, with the pivot element, right? So we compare 14 and this value 42. So we say that this a of j is less than the pivot element, which is 42, right? So what happens in this case? If we have a of j, as we have written here, a of j is less than equal to pivot element, then we increment the value of I and we swap, right? We do I plus plus. Now I was earlier 1, it will now become 2 and we again swap. So what do we swap? We swap a of I and a of j, right? Now what is a of I? I has now become 2, so a of 2 and a of j is currently 3. Okay. So what is basically happening here is you are going to compare each element with the pivot element. If that particular element that you are comparing with pivot is less than or equal to pivot, then you increment the value of I and swap a of I and a of j. Otherwise, you do nothing and move to the next iteration. That is the simple algorithm that you are going to follow. Okay. So you are going to now swap a of 2 and a of 3. I has reached here. You are going to swap these two. So what is the output that you're going to get after this iteration? What will be the array? How will the array look like after this swap? After you swap a of 2 and a of 3? Yes, can anyone tell me how will the array look like? So we have 20 here. We are going to swap a of 2 and a of 3. So we have 32, we have 14, then 55, then 63, 79, 93, and 42. Okay, so now let me write down the indexes. Along with that, I'm going to write down where have I and j reached, and pivot is the same element, which is our last element. So pivot remains here. I has reached this particular position, and after this iteration, in the next iteration, when you increment the value of j is going to become 4, right? So j has reached here, I is at 2. Now, can anyone tell me what will happen in the next iteration where j is equal to 4? So you have j is equal to 4 and you have I is equal to 2. Now, when you compare a of j and a of the pivot element, what is it that is going to happen? Now you're going to compare a of j, which is a of 4, with the pivot element. So a of 4 is 63, compare it with the pivot element, right? So when you compare, you see that a of j is greater than the pivot element. right? So when this condition occurs, that is A of j is greater than the pivot element, then we do nothing. So the array is going to remain the same. So we say do nothing and the array remains same. Now we move to the next iteration where j is 5, I remains at 2 only, j has reached 5, I remains at 2 only. Again we compare A of j, we see that A of j again is greater than the pivot element. So 79 is greater than the pivot element, which is 42. So again we do nothing and move to the next iteration, right? So in the next iteration we have j is equal to 6 and I remains at 2. So we have reached at j is equal to 6. Again we compare A of j, which is 93, and the pivot element, which is 42. We see that A of j is again greater than the pivot element, right? So we do nothing. Now, so now what happens? The loop that we had started off with j is equal to 0, and we said that we are only going to go up till the last index minus 1, which is last index was h, high index, high minus 1, that is till 6 only, because at 7th we already have the pivot element. So once you have completed this up till this j loop, you started off with 0, 0th index, and went on up till 6th here. So when you have actually done this, gone up till j here, and this loop ends, the jth loop ends, then what is it that you're going to do? That means that it is now time to place the pivot at its correct position. Okay, so now you place the pivot element at its correct position. So after, let me write this down, after j loop ends, place the pivot at its correct position. And how do you do that? You simply swap. So how will you place the pivot at its correct position? You will perform this swap. So this swap is going to be A of I plus 1 and the swap of A of the or the pivot element, or A of high. Okay, so I is currently at 2, so that means I was at 2, so that means A of 3, you swap A of 3 and A of h is 7, which is where the pivot element is stored, right? So you swap A of 3 and A of 7. What is A of 3 and A of 7? A of 3 is 55 and A of 7 is 42. So you are going to swap these two numbers, which is A of 3 and this pivot element. So now once you swap, let us write down what the array looks like after you have swapped it. So you have 20, 32, 14, and in place of 55 you are going to have 42. Okay, so you have 20, 32, 14, 20, 32, 14, then you have 42, which is the pivot element, then you have 63, 79, and then you have 93, and at the position of this 42 you are going to replace it by 55, so you have 55 here. So this is how your array looks like after the pivot element has come to its correct position. Okay, so let me again write down the indexes. This is 0, 1, 2, 3, 4, 5, 6, and 7. Now what happens after the j loop ends? What happens? What you said that I have now placed this pivot at its correct position. So this pivot is at its correct position. So now you are going to consider this sub-array differently and this part of the sub-array differently. Why? Because you say that pivot, this element, which was earlier the pivot element, has now been stored at its correct position, and this position will not change in the output. So in the output, in the sorted output, this value 42 is going to remain at its position. Okay, so the next thing that you do is, now you consider this as a different subarray, this as a different subarray, and you simply again perform quicksort on this subarray and then quicksort on this subarray as well. Okay, so up till here is everything clear? Up till here we are going to move ahead and perform quicksort on this subarray and this subarray as well. But up till here, is everything clear to everyone? Have you understood where we have reached? We have run the J loop once, and after it end, we replaced the value of pivot with its correct position. So we place the pivot at its correct position after the J loop end once. Okay. Okay. Okay, so let us move ahead, perform quick sort on this half of the subarray and this half of the subarray again. So what do you do here? Now this subarray is in itself an array. So you again, when you want to perform quick sort on this, you are going to consider the last element like we did earlier. You consider the last element as the pivot element and you start with j is equal to 0. So you say that for j is equal to 0, for now you have only this subarray which you are going to perform quick sort on. So you say for j is equal to 0, and for the value of I, this, which is I is equal to -1, you are going to start off, and again what do? You compare a of j, which is currently a of 0, with the pivot element, and you see that this value j, a of j, is actually greater than the pivot element, right? So when this condition occurs, you do nothing and move ahead. So when you move ahead, you increment the value of j, which is the next iteration of the j loop, and when you increment the value of j, value of I is going to remain same because nothing happened in the previous iteration. So j has now reached here. From here j got removed and j reached here. Again you compare a of j, which is a of 1 now, with the pivot element, and you see that a of j is again greater than the pivot element. So again you do nothing, and now you see, like we said earlier, for the j loop iteration, j is going to start from the first element, which is this element, and go on up till the index of the pivot -1, that is only up till this element. And then what will you do? You will place the pivot at its correct position. So this means it is time that you swap the value p. What do? After j loop has now ended, so you swap a of I plus 1 and a of what was that? A of h, right? So you swap these two values. So I is at -1 currently. So I -1 is going to become a of 0, and a of h here is going to be the index of this, which is a of 2. So now you swap 14 and 20. So what do you get? You get 14, 32 and 20. Now again what happens? Since now again you say that the pivot has come to its correct position, you say that pivot is going to remain at this position, and I am going to now sort the remaining array. So in the remaining array you have these two elements only. So for these two elements, again, you consider the last element as pivot, and j is going to start from this element now. When you start j with this element, again, what do? You compare a of j. A of j is greater than the pivot element, so you do nothing and come out of the j loop because you have already covered all the indexes for j, and then you simply swap a of I plus 1 and a of h, right? So you again swap these two numbers, the pivot element comes at its position, so you have 40, 20 and 32, right? Once you swap these two elements, now you have pivot again at its correct position, so you consider this part of the array as sorted. 14 was earlier sorted, 20 is also now sorted, 32 is also actually in the sorted position. So you have this half of the subarray, 14, 20 and 32 up till 42 here is sorted, right? This half of the subarray is now sorted. Now you will perform quick sort on this subarray as well. So can you tell me what will be the value, the array, how will it look like after each iteration? So now do this yourself and tell me one by one what is going to be the value at each position of the array after each iteration. What will happen for this value where j is going to start from here and this is going to be considered as a pivot element? Yes, j is here and p is going to be considered as the pivot element. The value of the value of I is -1, but so the first thing here is that whenever you are going to swap the value of j and swap the value of pivot, so whenever the j loop ends and you swap the value of pivot and a of j, then what happens? It is going to be another recursive call. So in the other recursive call, when you call quicksort with this piece of subarray, you start off with I is equal to -1 and this j is equal to 0. So this is considered as a separate array here. Okay. This part of array is considered as the separate array. So obviously you always start with I is equal to -1, and when it is time to swap it, you always say a of I plus 1. So when you swap before the recursive call, you say a of I plus 1. So that is what is in the actual algorithm. Okay. Yes. So has everyone understood up till here? If yes, then go ahead and tell me about this. Okay, so Rishabh says that it is going to be 55, 79, 93 and 63, which is correct. How? You are going to compare A of j. Now A of j is greater than the pivot element, right? Then you are going to compare with this value of j. It is again greater than the pivot element. This is also again greater than the pivot element. All three values are greater than the pivot element. So no change in this array occurs, and simply after the j loop ends, you swap these two values, which is you bring pivot at its correct position. So 55, 79, 93 and 63. Okay. So this is another recursive call wherein pivot has come to its correct position. Now you are remaining with with this subarray. So now what will happen with this subarray? With this subarray, this is considered as pivot, this is considered as j. Again, you compare with a of j. A of j here is greater than the pivot element. This value is also greater than pivot element. So simply nothing happens and you change the values of j and pivot element. So you have 55, 63, 93 and 79. Then you have this subarray remaining where pivot element is this and j is this. Again, when you compare, you place the pivot element at its correct position. So you have 79 and 93. Okay. So finally, When you have this here, you are going to have 42, 55, 63, 79, and 93 as your final output of quicksort. Okay, so is it clear to everyone how is quicksort happening? Can you now run quicksort algorithm on any given input example? Will you be able to do it now? Any doubts to anyone? Okay, so with that, let us understand about this other features of this. So if we talk about the time complexity of quicksort, we say that it is going to be order of n log n, same as that of merge sort, and the space complexity here in this case is going to be, since we do not consider any extra space in quicksort, we say that the space complexity is going to be order of 1. Now if the space complexity is order of 1, we call it a in place algorithm, which is it is not working using any extra space, and we say that this particular sorting algorithm, which is quicksort algorithm, is not stable. What do you mean by not stable? Not stable means that equal keys are not going to maintain the same relative order. Okay, quicksort is not a stable sorting algorithm. Let us consider another example for quicksort, and this time you are going to um, run quicksort on it, and then tell me what is going to be the output after each iteration, let us say. So let us say, for example, I have 2, 5, 3, 1, 6, 7, 0, and 4. Let us say that you have this example, and now I want you to run uh, dry run quicksort algorithm on this, and then we are going to move ahead. So this is what you have. Now tell me how it is going to move forward. If this is the pivot element and you start with j is equal to 0, and you have I is equal to -1, say, for here, and let me also write down the indexes. So you have okay, so yes, move ahead and tell me what will you do, and after each iteration, how will you get a certain array arrangement. Yes, go ahead, everyone. Try this example. Yes, so there is this question by Aman, which is how is quicksort in place if we are taking we are doing it using recursion and we are going to take extra space on the stack. So like I said in the beginning of the class, when we talk about recursive algorithms, we do not actually consider those recursions as a part of extra space. That is only for you. I have told that these examples that I told you, in which we were considering space as some extra space on the stack, like we considered here as well. We are doing that in order to just understand that yes, it is going to take some extra space, but it is not actually considered. Why? Because recursion is a kind of a way in which you can sort or not only sort but perform any particular algorithm. So the space on the stack which is taken by, let us say, a function call is not always considered as extra space. Why? So the first thing here is, if we perform recursion, obviously there is going to be an extra space, but any particular algorithm can also be solved using an iterative version. So you always have an iterative version for merge sort. Say for example, it can also be performed using recursion and can also have a iterative version. For the iterative version, there is not going to be any extra space on the stack. Okay, so yes, are you moving ahead with this example? Can you tell me what will be the next, how will the array look like after the first iteration? Okay, so when we are doing a of I greater than p and we do nothing, then why are we swapping these values? So the swapping that you're talking about, which is a of I plus 1 and a of h, is done after the j loop ends. So after, let us say, this j has reached this position after every iteration of the loop, then you are going to place pivot at its correct position, because you say that now I have compared it with all the elements of the array, so it is time that I have to switch or swap it with the index where you have I plus 1, because that is what it is the correct position for this element pivot. Okay, so there are answers here on the group. So let us move ahead with this. So you compare with j is equal to, let me change the color first. So we say for j is equal to 0 and for I is equal to -1. These are the current values of I and j. You are now going to compare a of j with the value p. So you say a of j here is less than the pivot element. So what do you do when it is less than or equal to the pivot element? What do you do in that case? You are going to increment the value of I. So I now becomes 0 and you swap a of I, which is a of 0, and a of j, which is a of 0 again. So after the first iteration, the array looks same, which is, since I and j have the same value, so there is no change in the final output of the after this iteration, right? So this is what happens after the first iteration. Let us move ahead and talk about the next as well. So in the next iteration, the value of j is going to change. So j has now come to this position here and I is here, right? So what do you do? Again, you compare the value of a of j and the pivot element. So you say that a of j, which is a of 1 currently, here you have I is equal to 0. A of j is is greater than the pivot element. This is the pivot element, right? So what happens in this case? You do nothing, you just go ahead and uh, simply change the value, right? Is that correct? You go with j is equal to 2, so j reaches here. Now you have a of j which is A of 2, is less than equal to the pivot element. So in this case, you increment the value of I, you do I plus plus. So I now becomes 1 and you swap A of j and A of I. So A of I is A of 1 and A of j is this. So you swap these two values. And now what is it that you get as output? You get 2, 3, 5, 1, 6, 7, 0 and 4, right? So what are the values that you just swapped? You swapped these two values, right? So again, if I go ahead and write down the indexes and then move ahead, this is pivot and j was earlier 2, it will now be incremented and it will reach 3 and I has now reached here, right? Again, what do? You compare. So you compare, so let me write down the values of j and I as well. So j is equal to 3 and I is equal to 1, right? You compare A of j, so A of j, which is A of 3, is 1. 1 is less than the pivot element, right? Pivot element is greater than this value. So what happens in this case? If you have this value, A of j is less than or equal to pivot element, what do? You simply increment the value of I, which is I now becomes 2 and you swap these values. So you do A of 2 and the next element that you have is A of 3. So you swap these two values, right? So you have 2, 3, 1, 5, 6, 7, 0 and 4, right? Is everyone with me? What do you have now? You have j at 4, right? And where is I? I is here. Again, you compare A of j. Now, A of j is greater than the pivot element. So, in this case, what do? You do nothing and increment the value of j. So, you increment the value of j now becomes 5, I is at 2. So, what do? Again, you compare A of j. A of j is again greater than pivot element. So you do nothing and you again increment. So increment the value of j, I is at 2 only. Again you compare. This time A of j is actually less than equal to the pivot element. So what do? You increment the value of I. So I now becomes 3 and you swap A of j. A of j, j is 6 and A of I. A of I is 3. 6 and 3. These two elements, 3 and 6, right? So what is now the array? You have 2, 3, 1, 0, 6, 7, 5 and 4, right? You swap these two values and let me just write down the indexes again. So 0, 1, 2, 3, 4, 5, 6 and 7. Pivot was here. J had reached here and I was at 3, right? Now what will you do here? J has actually reached the high index minus 1, the index which is high index minus 1 position. J has reached here. This means the J loop has ended. So for those who did not understand why are we swapping A of I plus 1 and A of H, now is the time. So once J reaches here, J reaches the index where pivot is stored, pivot minus 1 index. When it reaches here, that is when the J loop ends, you are going to swap the values A of I plus 1 and A of I, right? Which in this case means A of 3 plus 1, which is A of 4 and A of 7. So what is the array that you have now? You have 2, 3, 1, 0. At this index 4, you are going to have the element 4. Then you have 7, 5 and 6 here. So what are the values that have changed their, swapped their position? 6 and 4, right? So now you consider, so now you say that the pivot has come to its original position, which is 4 was the pivot element. It is now in its original position, and you consider this half of the subarray as different, this half of the subarray is different, and then again go ahead and what do? You perform quick sort on this separately and quick sort on this separately, right? The partition of the array has been done. Partition is done based on the pivot element. Pivot element has come to its original position, which was the first recursive call. Now you make another recursive call. Again, you consider this as the pivot element and this as J. You compare all the elements and you see that I will now have to swap this. So you have 2, 3, 1 and 2 here. After this, you perform quick sort on this. Again, you consider this part, this pivot element at its position. You now are going to perform quick sort on this. So when you perform quick sort on this, this is the pivot element and this is the jth position. So when you perform, when you see here, you see j is greater than the pivot element, do nothing, j reaches here. Now when j reaches here, you see that a of j is less than pivot element, so you swap these two values. So when you swap these two values, you have 1, 3 and 2, right? And this part of the array is sorted up till here. Then you perform quick sort on this. You have 0, 1, 2 and 3 because these two values are going to swap. Now up till here, 0, 1, 2, 3, 4, up till here the array is sorted. Again you perform quick sort on this as well. So when you perform quick sort on this, you have 7 a of j, which is greater than the pivot element. So nothing happens. A of j, when j reaches here, is less than the pivot element. So you swap. So what do you swap? You swap 7 and 5, right? So you have 5, 7 and 6. Now next 5 is at its correct position. You are going to perform quick sort on these two elements. Then you see that these two elements are going to be swapped. So you have 5, 6 and 7. In the final output, you have the sorted array, which is 0, 1, 2, 3, 4, 5, 6 and 7. Right? So has everyone, we should also update the value of the pivot index. So pivot is basically storing the value, and not pivot element that you consider is going to store the value of a of h. Okay, so it is going to depend upon the value of h that you consider high. So the value of high for this particular array, so earlier when you had the complete array, h is going to be here, which is 0th index and then high index. But when you consider this particular array, in the next recursive call, this is going to be the low index, which is equal to 0, and h index is going to be here, which is 3. So this element is completely going to depend upon the value of high index. That is why you have to, for keeping a track of the values of the pivot element, you are going to have the high and the low index. Okay. So yes, has everyone understood? Any doubts to anyone? If there are no doubts, then we are going to end this class for today, and we are going to look into certain different questions in tomorrow's lecture. We are going to completely have a programming based lecture tomorrow. We are going to discuss logic for different questions. Okay, so if you have any doubts, then post them in the group. Otherwise, we are going to end the class. Okay, so how are we getting 0, 1, 3, 2? Okay, so when in the first iteration here you have this, you have 0, at you compare this with pivot element with a of j. Everywhere you see that a of j is greater than the pivot element, so you do nothing when you are running the j loop. But after that, you are going to swap the value of pivot with the value of a of I plus 1. So you have 0, 3, 1, 2 in that case. After that, you have this part of the array. For this part of the array, what you're doing, you're considering this as the pivot element, this as j element. Now you see that this j element I will again be at -1. For this half of the array, you're considering only this array. Pivot is at 2, I is at -1, and j is here. Okay, so what do? You compare a of j with pivot element. You see that a of j is greater than the pivot element. So you do nothing. J comes here. Now when j comes here, you say that a of j is less than the pivot element. So what do? You swap. What do you swap? You swap a of j and you swap a of I plus 1. Right? So I comes here. What do you do when the pivot element is greater than a of j? What do you do in that case? You first increment the value of I, you do I plus plus. So I from -1 goes to this position here, 0. This is, let us say, 0, 1, 2. I comes here and you swap a of j and a of I. So you swap these two values, and when you swap these two values, you get 1, 3, and 2. So that is how you are getting this. Okay, I hope that was helpful. Okay, if there are no more doubts, I'm going to wait for another 5 minutes. You can post your doubts here. If there are no more doubts, then we are going to end the class for today. For those who do not have any doubts, go ahead. As a part of your homework, you should implement merge sort and quick sort algorithms and understand. Okay, so before ending, there is another thing that I wanted to let you know. So as a part of your homework, you should go ahead and try an example where the array is sorted in decreasing order. Okay, or let us say if the array is completely sorted, and then try this same thing. So let us say you have 16, 14, 11, 9, 7, 5, and 2. In that case, in this particular case, the worst case of quicksort occurs, which is going to take order of n square time. So the worst case of quicksort algorithm is going to take order of n square time, and that is going to occur if the array is sorted or if it is reverse sorted. Why do we use quicksort if there are other easier sorting algorithms? So quicksort, as you know, is something which takes less time. So the time complexity of quicksort is going to be, let us say, n log n for any sorting algorithm. For other sorting algorithms, you have the time complexity as either order of n square, or that particular sorting algorithm is going to consider extra space. So if you compare merge sort and quick sort, merge sort takes the same time, but it is going to actually take some extra space. So if you do not want any extra space and you want to have your sorting in less time, then you can consider order of n square, quick sort, which is going to take order of n log n time. Okay, so the questions that were a part of yesterday's test, we are going to pick that up tomorrow in the tomorrow's class, because tomorrow we are going to be discussing all related programming questions which are related to sorting. Uh, for now, we don't have much time to pick that up, but we are going to do that tomorrow anyway. Okay. Any other doubts, anyone? Apart from this particular question that you're saying, which is the first question in the in yesterday's test. So yesterday's test had two questions: swapping numbers and sorting. We are going to look into both of them, and also we are going to look into one of those questions that I had asked in one of the tests previously, which was to sort some certain numbers, but it was not really happening for large values, right? We are going to discuss that as well. Okay, so if there are no other doubts, then let us end the class for today and let us meet tomorrow and discuss all of these questions. Thank you, everyone.